So I'll give you a little bit of an overview on the Lunar Environment Monitoring Station for Artemis 3 or LEMS A3. So this is an investigation that has been in the work for 5-6 years now. We're waiting for. Okay, awesome. I said this is an investigation that's been in the work for 5-6 years in development and technology maturation. So we're really excited to have this now being implemented for flight. It's a contribution of several institutions, University of Maryland, Baltimore County, University of Maryland, College Park, University of Arizona, and Washington University in St. Louis, with obviously a big contribution from NASA as the implementing agency, technical agency, or NASA Goddard as the implementing technical center for LEMS. Next. So what is LEMS? So LEMS in its concept, it's a lunar environment monitoring station. So it's a compact, autonomous, self-sustaining geophysical instrument package. In the case of Artemis 3, it's a seismic suite that was designed to enable multi-year in situ monitoring of the moon seismic environment. We designed it, and the visual concept we always had of LEMS is the buoy for the moon. We want to do science for long term, but with a rugged package with low overhead for operation that allow us to build many of these eventually and lead to multiple packages deployed on the surface with low cost and high longevity. To do that, the package by design is a self-powered, self-managed, and self-communication flight system. So we're not relying on assistance from a landing vehicle or a crewed mission to operate for long term. It conducts its science observation on the lunar surface continuously, both day and night. We don't only survive the night, but actually we operate at night. And for the case of Artemis 3, we are carrying 2 seismometers, a seismic suite with 2 seismometers that complement each other with the goal of characterizing the lunar seismicity and the internal structure of the moon. The package is about this size. We're actually right now going through a very intense design phase to accommodate LEMS on the human landing system, which sees some of those dimensions shrink in a bit, but overall we are about 26 kilogram package. Next. So why LEMS for Artemis 3? It's really it comes from 2 basic premises. The first one is that in order to do good seismology on the moon, we require to basically carry out observations for long durations, months or years, which are currently beyond the duration of the Artemis crewed mission of a few days. And so we need some packages to be left behind to last beyond just the duration of the Artemis mission. That was the case for Apollo, for example. The bulk of the science from Apollo came from the long-term observation left by the LSEP carried out by the LSEP left on the surface. The second idea behind LEMS for Artemis is to provide a standalone package that minimizes the need for deployment during EVA for the astronauts. So as you all familiar with, the LSEP was a distributed system with a station with a central node that does communication and does power management for all the instruments. In one location, you have a power source. In another location, you have sensors distributed on the surface. And that was EVA intensive. We wanted with LEMS to have everything self-centralized, be a single package, basically a science in a suitcase type experiment where the astronauts can put the package on the surface and everything is already deployed with it. Next. Our science goals, as I said, LEMS target really to measure characterize the lunar seismicity from various sources that both operate at local and global scales. All these sources require long-term observations, and so we baselined a minimum, and we baselined the nominal mission duration of 3 months after deployment on the surface, with a target goal of operational duration of 2 years. That allows us to observe not only the deep moonquakes, which we expect to be quite abundant, both from new cluster sources or past still active cluster sources that were observed during Apollo, but the more rarer shallow quakes and seismic events from micrometeoroid impacts and thermal stresses. And to able to do that, our 3 months baseline mission duration allows us to at least get to enough statistics to pretty much cover all these sources. Obviously, observing for 2 years, you get 2 diurnal cycles on the moon that provide repeatability, that provide 2 full years of repeatability, but inherently LEMS has no consumables, so the 2 years limit is purely what is driven by a science goal. The package is designed to last as long as the electronics will hold. There is no consumables built in. And so by characterizing the lunar seismicity and the sources of the lunar seismicity, we get to hopefully get to do to establish local crustal and mantle structure layering at the South Pole, but also go into a deeper in the moon, trying to constrain the core state composition and structures. And LEMS is still operating as a single station, but we're cognizant that if we're lucky enough, by the time we land on the surface of the moon, FSS will be on the far side, will hopefully still operating, and we can get to really very interesting seismology analysis by having a multi-station observations. Our third goal is to assess the local and global seismic hazards of the South Pole. Obviously, Artemis, we're going with Artemis to stay. And so if we are planning to build structure on the South Pole and permanent settlements, one want to understand really what's the seismicity of the South Pole and the hazards. There are I already identified scarp faults in the South Pole, but we still don't understand what hazard they pose to long-term activities in that location. Next. So the LEMS package itself, it's all built in one unit. It's what you see on the left is the LEMS with its thermal blankets, which are all the orangey layers. But when you remove them, you see the figure on the right, which is the internal components. LEMS is of the size of a carry-on suitcase that Delta Airline will let you hopefully carry on board. It's composed of a main bus that hosts the brains of the station, hosts its avionics system, this comm system, and its batteries, which allow us to survive and operate at night, but also carry the solar panels in the front and all our telecommunication antenna. We have 2 low gain antennas and 2 medium gain antennas, which allows us to do communication at a fairly high data rate. The science sensors themselves are the broadband and the short period sensors built by University of Arizona. I'll get to those a little bit later. Are attached to the side of the station. The station is carried like a suitcase by the astronauts, put on the surface, and then the 2 seismometer get detached, reel to some distance from the station and deployed, and we'll talk about that also in a little bit. The station is designed to be autonomous, so there is no link either in data or power to the human landing system. Once it's deployed, it links directly to the deep space network, and at which time we start commissioning and put it into a science operation mode. Next. The SP and the BB seismometers, as I said, these are built by a partnership between University of Arizona and a private company called Silicon Audio in Arizona. These are triaxial low noise optical seismometers. They're capable of detecting passive seismic signals over broad frequency range. The SP and BBB complement each other. You see on the right a spectrum plot that shows the expected responses of both seismometer compared to, for example, the LSEP SP and the LP seismometer from Apollo. And we put in notionally in the blue shaded area is the already explored part of the spectrum by Apollo. This is where we basically have identified seismic events, but it does not mean that the white area does not have any signal in there. It remains unexplored. So as you can see, our SP and BBB will expand that little coverage in the spectrum domain for these seismic events. Each seismometer carry identical sensors. There are three sensors, one for each axis, that are packaged in such a way to have each sensor oriented in one specific directions. The SP is a little bit smaller than the broadband seismometer. They are about one is about the size of a cocaine, one is the size of basically a pint of milk box, and but they are redundant sensors inside. So should we lose one axis, the seismometer still operate with the remaining axes unaffected. Next. We started actually fairly recently working on the ConOps for deployments during EVA, working with the flight operation directorate at JSC. And we really have started really drafting what our ConOps for deployment will be. The basic idea behind deploying the seismometer is that we want the SP, which is the smaller seismometer, to be dropped in an existing borehole made by the astronaut to get a core sample. So we will have to coordinate the location of deployment of LEMS to be near an existing borehole or a future borehole that the astronauts will do. But that borehole has to exist by the time we deploy the SP seismometer. The idea is to use the same tools used to extract the core sample, fit in the SP seismometer at the end of the tool, and drop it back into the hole. Ideally, the seismometer will be pushed down 30 to 40 centimeter deep. It will be pushed in snug into the hole, so it will have a good mechanical contact, and then the tool can be released and the seismometer will remain on the bottom. The seismometer will be attached to the main station by about 9 to 10 meter ribbon cable, which will carry the power to the seismometer, but also carry out the telemetry from those sensors. Next. For the broadband seismometer, we're baselining that it will be buried in a shallow trench. So we're asking the astronauts to make us a nice 40 to 50 centimeter by 20 centimeter deep trench. I'm putting a picture there, a trench done during Apollo 17. This is the type of trenching we're looking for. And then we'll ask the astronaut to drop the broadband seismometer in the trench and then bury it. The reason we would like to have that, I'm sorry? 5 minutes left. Sure. The reason we would like the broadband seismometer to be covered with 20 centimeter regolith, it's for thermal stability, to provide thermal stability, especially at night, for the sensors, but also to be a little bit to mitigate a little bit the effect of surface noise and scattering. Next. This is our notional deployment site layout. So we baselining that we will be deployed on the north of HLS. Unlike LDA, we don't want to be in the shadow. We want to be actually in the sun. We have solar rays that need to be illuminated in order to operate. So we want to be away from the shadow of HLS. We also want to be far enough from the blast area. This is a topic that's still being investigated, how far we need to be. There is quite a bit of effort across the entire Artemis program to assess what's the blast area of the HLS. And so notionally will be somewhere far enough that we are safe from when the HLS ascends back to leave the moon. We would like to be in an area that is of a shallow slope, less than 10 degrees. So our LEMS can align itself and its antenna and solar rays can be pointed properly. And then somewhere in the vicinity, we'll have the SP borehole and a broadband seismometer trench. Notionally, they will be at the east of LEMS because that's how the cable are designed, but really nothing preclude us from putting them either in the back or on the west side. So obviously, there are a lot of logistics that goes into defining the deployment site layout. This is always still notional based on LEMS-centric requirements, but we'll hopefully be defining that in more detail in the next few months. I think this is my last slide. Any questions?
Time for a couple of questions.
Oh.
Hi, Dave Blewett, Johns Hopkins Applied Physics Lab. What do you expect that extent of the landing system blast zone to be?
So it's hard to tell because we still don't know really the characteristics of the HLS propulsion systems behavior in the lunar environment close to the surface. So that's being studied. But if if past missions are any indication, so Apollo 12 landed near one of the surveyor landers, and I think the surveyor was like 120 meters away, and they retrieved some parts back, and they did a lot of documentation and photography on what's the state of the surface of that lander, and there was quite a bit of sand blasting. And so there is no real dynamic pressure away from the nozzles of a vehicle. So if you are 10, 20 meters away, you're most likely not going to feel any gas pressure. But it's the blasting of small micron-sized dust particles that get accelerated to up to a kilometer per second. That is the risk. So we're looking at mitigating that, possibly putting metal sheet face on the back of LEMS as almost like an armor in the back. It's what we're looking at, but that comes at the expense of mass, and so there are a lot of traits in there. But that's being assessed. It's a serious risk that we're trying to understand and mitigate.